Webinar on eliminating the trial and error cycle using Ansys Sherlock to predict PCB life cycle. In this session, we'll discover how Ansys Sherlock transforms PCB design from reactive testing to predictive reliability engineering. So what you'll learn in this session is the real cost of failure, automated ECAD-to-FEA, and the physics of failure insight. And also you'll learn something about multiphysics integration. We are pleased to host Mr. Srinivasagam, who is a seasoned professional with over 12 years of experience across aerospace, machinery, and semiconductor industries. With deep expertise in water fab equipment and lithography machine product development, Mr. Srinivasagam brings strong capabilities in product validation, engineering standards, and complex project execution. His pre-sales and customer-facing experience enables him to effectively bridge technical solutions with real-world client needs, driving innovation, reliability, and long-term partnership. Join us for this insightful session. Welcome, Srini, and you can take over the session now.
Thank you, Tanvir, for that brief introduction. Good afternoon to all the participants, and thank you so much for joining this webinar in spite of your busy work schedule. Thank you for that. So I hope my screen is visible. Can you confirm?
Yes, it's good to go.
Okay, thank you.
If any of the attendees are facing some problem, kindly request you to please mention it in the chat and we will address it immediately. Thank you.
So once again, good afternoon all. Thank you so much for joining this webinar. So this webinar is presented directly in collaboration with SoftCell and Ansys. So this is a part of a reliability engineering series webinar, which we are planning to conduct through the year. So in today's session, we will be primarily learning about how to eliminate the trial and error cycle using Ansys Sherlock to predict the PCB life cycle. And apart from that, various reliability like thermal reliability, mechanical reliability, and electrical reliability. What are all the things we need to take care? And what are the major challenges in the PCB design, and how Ansys Sherlock helps you to unlock your true potential, and how you can focus towards the design rather than worrying about the failure of the product. So having said that, in today's agenda, what we will be covering is, we will be covering what is a PCB, what are all the basic PCB design process, what are the challenges in the PCB design, challenges in the PCB manufacturing, or what is the Ansys solution product line we are having. And there will be a quick demo on the Ansys Sherlock tool, and followed by Q&A. So in between, throughout the session, at any point of time, if you have any queries or if you would like to have it addressed, we request you to drop in the questions in the chat window. We will be taking the answering the questions at the end of the session. So basically, what is the PCB? So I know it's a very basic question, and you are all like seasoned professionals who are day in day out handling them. But just to set the context here. So basically, a printed circuit board is used to mechanically support and electrically connect various electronic components, which is getting mounted onto this PCB board, which is primarily made of FR4 material. So how does this PCB work? Is it uses a conductive pathways, pads, or signal traces, which are etched from the copper sheets laminated onto a non-conductive substrate. Basically, this is a substrate is a like a thin laminate on which we mount all our active and passive components. And this substrate is a non-conductive material, basically. And PCB is like an integral part of our life, day in, day out, whether right from our mobile phone, tablets, smartwatches, wireless chargers, and power supplies. You name it, and you have one or the other way you can find the PCB being used in that product. So in this PCB, we also have a multi-material, multi-layer boards forming the stable foundation for the PCB complex PCB assemblies. So this PCB is responsible for directing the current flow between the active and passive components. So here we need to understand like what do we mean by the active component and the passive component. So active components are used to generate energy, whereas passive components are used to store the energy. So some of the active components are transistors, diodes, ICs, amplifiers, sensors, and crystal oscillators. Whereas when it comes to passive components, we have resistors, capacitors, inductors, transformers, and relays and fuses. So having said that, so basically we start with the PCB design process. So there are three different levels in which we do the PCB design process. We majorly classify into initial planning and schematic phase. Then we go for the PCB layout, routing, and design verification. Finally, we go for the manufacturing preparation and delivery. So what are all the things we cover in this PCB design processes? We start with understanding what is the board requirement, what is the primary application where this PCB is going to be used. And we develop the various CAD library parts which gets into the PCB board, and we create the schematic, and we do the schematic simulation requirements. And having done with the initial planning, we move on to the PCB layout, routing, and design verification, where we have the CAD tool setup, PCB size consideration. We design our PCB stack up. What is the stack up we need to use? Whether it's a 3-layer or 4-layer or 6-layer or 8-layer board, what we are going to use. We define the design rules and the DFM requirements. We decide on the location where we need to place our components. We route the traces. We decide on the power and ground nets. We insert the drill holes, add various rough disks and labels and identifiers. Finally, we verify it in the simulation and we complete it with the final design rules check. And till this step, we are only focusing on the initial design. So you can see like major 70% of our time is getting spent into the initial design phase. And once the design is validated and it's good to go, then we go for the manufacturing part of it, where we concentrate on the PCB manufacturing file creation. We send the board for the fabrication, then the vendor will source for the components. While designing only, we need to check. It's not like we can use any component for any application. Basically, we need to also understand what is the lead time for that particular connector of the assembly. So based on that, we need to collaboratively work with the manufacturer or the vendor to decide on the lead time of the sourcing components. We need to do the quality check and visual inspection. Finally, we package and deliver it. So in the PCB manufacturing process, primarily it starts with the pre-production engineering, where we have the basic board layout and other things defined. Then we go for the inner layer imaging, followed by the etching process, followed by the photoresist stripping. And we do the inspection and post-etch punch. So this is a repetitive process. Depending on our design, this process will get repeated. And the next phase, we go with the alternate outside coating. So we will, based on the number of layers, we repeat this process. Then we go with the drilling. Then we go with the metallization of the dielectric and the outer layer imaging. And we define the copper plates, that is the connections between these various laminate layers which we are assembling, how we are interconnecting each of them. And then we will go with the photoresist stripping, and we have a final etching, and then we have the tin stripping, and we have the solder mask application. Then we define the surface finish for our PCB board. We have the cell screen, and we do the electrical test, and then we do the routing and V-scoring. So these are the primary steps involved in a PCB manufacturing process. So coming on to the challenges in the PCB design. One first primary and foremost challenges we come across EMI and EMC challenges. Uh, as the name suggests, EMI is electromagnetic interference and EMC stands for electromagnetic compatibility. So these are the inductive coupling. What we evaluate in this EMI and EMC is we try to evaluate the inductive magnetic coupling and crosstalks, and what are the interference from the external fields, where it's going to used and how it is going to, say for example, if it is in a high density power board is there. So in that there will be a lot of electric field currents which is surrounding that PCB, which will have an impact on the PCB performance. So at that time we need to take into account and we need to validate our product for EMI and EMC compliance. Then we have the signal integrity. So as we know, with respect to the Moore's law adoption, day by day we have the high density circuits being printed, and it's driving the whole semiconductor phenomena. So this high-speed digital designs, as we need to carefully manage their signal propagation and return paths, and what is the trace geometry uh, we are going to use. Why we need to evaluate this is we need to evaluate its reflections. Is there any crosstalk or any noises coming? So all these things we will be evaluating the signal integrity. And third, we have the thermal performance. So as the high current density and current increases, so there will be a higher heat dissipation in the critical and densely packed boards and in high power applications, which if we have not done a proper thermal management, it can lead to a component failure and reduce reliability of our product performance on the field. So then we have the mechanical reliability. So we have different types of PCBs, basically rigid PCBs, flex PCBs, and depending on our application and requirement, these PCB designs keep on changing. So with respect to this, we have the complex assemblies which are prone to fatigue, vibration, and mechanical stress, which can cause cracks and solder joint failures and reliability issues. And the complexity and the scale, like so modern PCBs are feature multi-layer structures and the intricate routing, which needs to be carefully evaluated for its performance at the initial design stage. And there are numerous components which require accurate modeling, and the simulation also becomes challenging with respect to the increase in the complexity of the product. So coming on to the manufacturing constraints, we need to balance the design rules, size limitations, and at the same time, with respect to increase in precision cost manufacturing, what is how we are going to trade off between our design and at the same time with the effective manufacturing. So we discussed what are the challenges in the design. Now coming on to the manufacturing, high component density and miniaturization requires for a precise manufacturing process. Why? Because we have a very finer pitch between the components and the increasing assembly difficulty, which requires precise manufacturing process to be in place. And coming on to the thermal management, we need to have a higher lead-free processing temperatures and increased chip power densities, which create the thermal stress and which can lead to warpage, solder joint fatigue, and reliability issues. And coming on to the contamination and cleanliness, we have the electrochemical migration. And if we after this electrochemical migration process, if there is not sufficient cleaning taken into consideration, it can cause intermittent failures leading to no fault found returns and field reliability issues. And coming on to the mechanical reliability, we have the temperature gradients and the cyclic thermal loads, which can cause, which can which can induce the mechanical stress, deformations, cracks, and open circuits at the solder joints and interconnects, which at the end of the day leads to a failure. And apart from that, we have this micro via and plated through-hole reliability issues, which are predominantly found in the high-density interconnect boards. And these are majorly prone to failure, often causing in the open circuit issues. And it leads to the fatigue life prediction, which is critical for ensuring the product reliability. So how do we address all these challenges? So on the manufacturing front, we need to take into consideration the design for manufacturing guidelines as the best practices in the industry. What they follow, we need to adopt to it, and we need to follow a consistent manufacturing process and to minimize the defects. Second is we need to extensively adopt simulation and modeling techniques so we are able to get the products first time right and the reliability is matched with respect to our expectation. And third is process. We need to validate our process and testing. How we are, what is our manufacturing process? We need to validate it, whether it's as per the industry recommendations, and what is the recommended tests we need to do for each of these PCBs. And coming on to the design failure or common failures, what we observe is solder joint fatigue, which is due to reduced resistance to the fatigue with respect to the clear package type, which increases the risk of failure under thermal and mechanical loads. And we have the electrochemical migration, which can contaminate and can cause intermittent electrical failures, and which is often difficult to diagnose. And finally, we have the thermomechanical stress as well. With respect to the change in the cyclic temperature environment changes, it induces mechanical displacement and reliability issues, especially in the boards. So how do we deal with these challenges? So we have a solution from Ansys, which is called as Ansys Sherlock. So let's deep dive into what is Ansys Sherlock and what are all its capabilities. So with respect to Ansys Sherlock, Ansys Sherlock is primarily a reliability physics analysis tool for the electronic design, specifically with respect to the PCB, which helps users to mitigate the thermal shock and vibration and other risks involved in their PCB design. So Ansys Sherlock can be used in combination with the traditional Ansys product line like IcePack and Ansys Mechanical or CFD or Ansys Thermal Desktop. So it helps us to identify the thermal cycle fatigue, and the way it helps us to predict the solder reflow failures, and it helps us to evaluate during the shock and vibration loads how is the product going to behave, and for the different design and manufacturability. So basically, Sherlock predicts the product's failure throughout your design process. It all starts with the hardware specs, where we define the functional block housing connectors. So after done with the initial functional block, we will go for the initial part selection. So right from the initial part selection, Sherlock can help you with the selecting the right path for the right PCB and for the right application. So with the respect to housing and connectors, we go with the board outline. And in the board outline, we will be going with the schematic drawing and the initial part placement. So we later it translates into the bill of materials and final layout. And this bill of materials and final layout leads to a change management. So in all, right from the where Sherlock places a vital role is from the initial part selection, initial part placement. After you are done with your final layout and final bill of materials, it can help you validate your design And it does not stop only here. It helps you with the DFM activities also. As we go forward in this webinar, we will be looking in detail about what each of these things and how Sherlock will help you in those areas. So, reliability physics analysis. So basically, in the typical electronic design process, what we do is we start with the designing phase. We will build the prototypes, we test, and we go for the physical validation, and we observe the failures or the shortcomings, and then we fix it. So basically, this traditional life cycle, it holds true for 73% of the product development cost. And it's a like major pain for the companies to invest so much of time into this traditional approach. So what is the solution we have? So using Ansys Sherlock, we can reduce, say, for example, if you want to get the optimized design, if you want to do 10 physical prototypes, using Ansys Sherlock, it will help you to reduce it to 2 or 3. That is close to 70 to 80% of the time and money you are able to save. So it's not only like for your internal design, your end customers also as a value addition. What using Sherlock, if you are doing, it's not only like I am a manufacturer. Whatever I do build to print, whatever my customer gives, I just build it and give it. So given the scale of the development of the semiconductor and the requirements for engineering judgments going forward, there is a huge potential involved in for the PCB manufacturers to go from shift the focus from the traditional manufacturing more towards a design-based approach. So which will be a value addition when we, if you want to scale it to a global level. So having said that, in the Sherlock, it helps you to predict the reliability for your electronics. And it's like we have democratized the use of FEA as simple. So an PCB engineer himself can start using this after his initial design activity. So this, what is the major benefit is FEA can be used by all the engineers. We have unraveled reprocessing. So what? So that major input. So whatever tool you may be using for the initial PCB design, whether it's Cadence or KiCad or Allegro. So whatever maybe your design software is, you can, the ODB file is a primary input for the PCB analysis, where it helps you to where it helps you to evaluate the failure rate, plated through-hole fatigue, random vibration fatigue, solder fatigue. So all these things you can evaluate with the help of a single tool, and it's a single graphical user interface. You can do all these. So having said that, Sherlock reliability assessment through the design process. So like I mentioned earlier, we have the hardware specs, function block, housing connectors. So the same thing, it helps you to address the reliability issues due to environmental conditions such as shock and vibration loads, which may be acting on your PCB, and different thermal cycling. Say, for example, the PCB, if it is going to operated in an environment, cold environment like Kulu Manali, how your product is going to behave. And if it is going to be used in Rajasthan, where the thermal temperature abruptly changes. So due to this variation in the thermal cycling, the product needs to be validated for all these. So with the help of Sherlock, what we have done is we have democratized the FEA for all engineers to assess the reliability of their PCB, and which earlier used to be done by only the simulation experts. So it's no more the case like you need a dedicated simulation expert to perform these. these things or perform these simulations. So how we were able to do it is because of easy to use a GUI based interface. It speaks in the language of the electrical or electronics PCB design engineer basically. So which he can easily understand it. It just require 1 week or 2 weeks of training for them to adopt to the workflow, and right from that day, next day they will be able to deliver. So the PCB designers ensure that ideal critical component placement and selection is being optimized. Selection is being used, and thermal engineers, the temperature impact on cycles due to varying temperature cycle is helps to find the reliability of the product. And then later, whatever this results you are having, you can share it with your mechanical design team or with the electrical team to understand the key implications. So basically, now coming on to the user interface, it's a very intuitive GUI, allows user to quickly interpret and modify the inputs and review the critical outputs, such as the component time to failure. So basically, you upload your ECAD design, and then you apply the loads. You find the what are all the hotspots in your PCB board, and it's done. So with the help of uh, readily available models, we have best-in-class pre-processing techniques. Like the major challenge in the PCB board is like locating the geometric and material properties for the large number of components and the from the different supply data sheets and other sources. So what in Sherlock we have done is we have comprised everything and we have given everything in a ready-to-use template, and we have our own approved vendor list library. So where we have more than 50,000 plus parts available in that, various components, materials, PCB laminate material data. And it's not only that what default library we are having, you need to use it. It gives you the option to customize this based on your requirement, and you can evaluate it accordingly. So basically, to address the multiple failure mechanisms, like such as DFMEA, harmonic vibration, in-circuit test analysis, mechanical shock, finding the natural frequency, PTH, plated through-hole fatigue analysis, semiconductor wear out, solder fatigue, and what is the thermomechanical loading. So all these things you can find it using a single tool and single user interface. So it has a comprehensive analysis and the reliability predictions too, where we define the inputs based on the design requirements, where we apply the life cycle and the environmental loading inputs. So here you can see we have the sawtooth profile for our shock event. And then here we have the harmonic vibration analysis where we define the frequency versus load, what are all the things, and what is the thermal event, what is the thermal cyclic load which we are our part is going subjected to, and what are all the informative and actionable post-processing things. So here the major challenge is to define the board level reliability in a cost effective manner using standard approaches are often not sufficient. So we need to go with the reliability based physics analysis approach to predict the what is the mean time to failure for each and every component based on the physics based approach, and multi failure modes is essential of the hour. So here you can see like it gives us the overall combined risk, like what is our board's components, each of these component wise, it gives you the data so that all the red ones are like which is prone to failure, which is yellow ones are in the border range, green ones are good to go. So with the help of giving a component level data analysis results to you, you can easily identify where the critical zones are and how, what are all the different options you can design modifications you need to do to check your uh, reliability or how your component or board is performing based on the mill standard or whatever the design standard you are following based on your end customers Ansys as a solution to it. So here we have the vibration fatigue and thermal cyclic solder fatigue and PTS thermal cyclic fatigue. So basically, in consumer electronics, we often subject to a shock and vibration load life predictions. So basically, we have a 3D model here, and we have a shock profile, which we get it from the test data. And then we evaluate for the displacement plots. And then we have the table of reliability where we have the match displacement, match strain, what is the component time to failure, what is the failure probability, and what it gives a score for each of this, and what is the life prediction for this particular PCB. So coming on to the automotive side, we have various thermal cycling loads. So like I explained previously, you can view what are all the critical high temperature components which is getting placed onto your components, PCB board, and how it is getting connected. Layer wise details you can look into it. And based on the thermal cyclic profile, what is the uh, max temperature and what is the min temperature and which particular package on which desk. So all these data it captures from your ECAD design. So it's very easier for you to trace it out where exactly this particular which component is causing the going to fail and how you can address it. So coming on to the design for manufacturing perspective. So the major challenge in the design for manufacturing is the reliability considerations, such as which arises from the in-circuit test or bed of nail test. Physical testing is very expensive and time-consuming, whereas the solution what we have in Sherlock is the ICT, static structure-based simulation in Sherlock, where the component by component time to failure can be determined and the overstress predictions are also provided. So it gives us impactful insights to the design performance, which can help reduce the number of physical tests required for your product. So here you can see the fixtures at the corner of the PCB board, and we have 8 test points defined, 4 on the left and 4 on the right. So these are the test point and the support fixtures, and with respect to that, we have the displacement plot, and here we have the match displacement, match strain, what is the time to failure, and what is the failure probability. So it's you can ask, okay, what is the next action item for me? Your software is giving me the results. Okay, but how do I, should I go back all the way to my ECAD design and change everything and come back and again set up everything? So that's not the case here. So what happens is here we have the quick turnaround solution, which helps you to quickly design between your major areas where you can do the design trade-offs accordingly. So to give an example, we have taken 3 parameters. Like one is with respect to the how changing the pad size for that respective component is going to have an impact on the cyclic life and whether switching on to the package. So because at the end of the day, it all comes to the cost factor. So changing pad size may be a relatively less cost effective compared to changing the entire package and changing the entire laminate. So between these 3 options, it helps you to determine how the changing the pad size can help your product to increase the reliability of the solder solvability and how it can increase the fatigue life. So changing the package, how it is going to help you, and changing the laminates. Say, for example, here we had inch modulus of 27, and now we have increased it to 29,000 MP. So having changing these things, you can in a single go you can try various different options, and you can arrive at a conclusion which is a cost effective and best option for you.
We have another 15 minutes left for the session to complete. So I just
Yeah, thanks, Tanvish. So the reliability physics analysis, what it helps you to do is it helps you to avoid the redesign and retest due to failures, which is occurring due to constant temperature, thermal cycling, power cycling, vibration, mechanical shock loads. It eliminates to manufacture the defects and communicates the quality and reliability throughout your supply chain. So it increases your first pass yields from manufacturing. It helps to reduce the warranty returns in the field and helps you to predict board level predictions, help assess risk uh, associated with shock, vibration, thermal cycling, and other conditions. And you can couple it with the advanced Ansys solvers like thermal desktop and with respect to mechanical LS Dyna. So where you can do more broader assembly level simulations. So this simulation applications helps to do a better PCB design and getting it first time right. So here we have given few of the failure modes and the respective Ansys simulation tools here. One is on the thermal stress, mechanical stress, electrical stress, miniaturization, contamination, reliability prediction. When it comes to the reliability prediction, we go with Sherlock and multiphysics integration. For the electrical thing, EMI, EMC, we go with the SI wave, HFSS, EMI scanning. And for the mechanical stress, we go with the mechanical Sherlock and trace mapping. And for the thermal, we have ISPAC, SI wave, Sherlock, and mechanical. So having said that, I would like to quickly run through few of the things. So basically, here these are the few solutions where you can see like so here you can see the mechanical reliability solutions like Holder reflow due to the warpage issue when the tumble test how your PCB is going to behave. What are the shock and vibration, fatigue and fracture in the soldering? What is the moisture effect on the PCB and the drop test? When the PCB gets dropped, what is the impact on the board level? So having said that, I would like to take a second here to pass for any questions. Have we got any questions in the?
no, we haven't. So any questions from your end? I would like to ask the attendees if they have any questions. Kindly kindly add it in the chat box. I guess you can proceed.
Yep. I hope my explain is possible. Hello, Anvi.
Yes.
Okay. So basically, this is how Ansys Sherlock user interface looks like. So this is a graphical user interface area where whatever operations we are doing, it will be shown here. And this is a project schematic area where all the model tree and whatever operations we are doing, it will be shown here. And we have few options here, like how we can add a new project, how we can import an existing project, how you can import your ECAD file. So these are all the various formats which Ansys Sherlock support for you to import your ECAD file. And then here, these options gets enabled once we have the project. Excuse me. We have the project added. These options get enabled. And apart from that, we have the various libraries like laminates, materials. So here, if you go to the laminates, here you can see the list of manufacturers. And here you can see we have a very few vast amount of data with respect to different material. And here you do have filters based on the for filtering the and selecting the laminates based on the manufacturer material product name. What is the coefficient of thermal expansion, thermal conductivity, and based on your design requirements and needs, you can check it here. Similarly, once we go to the materials, the same way, we have different, very huge, vast amount of material manager from which you can select. So one more thing is it's not like only what we have you need to use only this. Here you have a option to add the new material where you can define the material, what is the type of usage, what are all the material density parameters. Once you have, you can define all of these and you can save it to the database and it will get saved locally. Similarly, we have the tools for the PTH fatigue, solder fatigues, and we have various advanced settings which we can change based on our requirement and the our needs. So basically, how do we start with the project? So here I start with the project webinar. So, as the project category. Save. So as soon as you can see, uh, once I add the project, I get this life cycle. So this life cycle is the area where we define all our loading conditions, whether it can be harmonic event or random migration or shock profile or thermal event. So all these things you can select it from this particular environment. So now we have added the project. Now we need to import our ODB file into this particular project directly. So I will go to import ODB directory. I will go to browse and selecting this particular directory and I select directory. And if here it asks for few parameters which you can define based on your requirement. And then you need to press on the scan archive. And here it will ask for the part description, subcircuit names, part number, etc. And here you can, once you give the archive, it will give you the list of things what it has read from that particular ECAD file, like circuit card, board properties, backup data, package data, solder marks, fill screen, copper layers, drill holes, everything. And once you hit import archive, you can see all the details are being imported into the Sherlock. Here you can see like just so here in the files mainly you can see all the copper layer silk screen and the drill hole data and the component details are being fetched out. And under the inputs, you can go to this double click on this parts list. And here you can see all the list of parts along with their respective rough disk and the part number, package, and the location, whether it's the top or bottom. All these details. And here you can filter it based on the location, like which components are on the top and which components are on the bottom of the PCB. All these things you can find it out. And apart from that, if you go to the stack up data, here you can find. So this is how many layers are there in the given PCB and what each of the how much amount of copper is there for each of these and how much, which is the power, which is the signal layer. So all these things you can check, and here you can double click, and if you want to change anything manually, you can change it as well here. And here it gives you the option to and flexibility to check and change the parameters. And once we go on to the layers, here you can see like what are all the different layers available in your components. So here you can see the top and the bottom components. And here you can see on the top side we have various rough disk and various capacitors and heat sinks, ICs, and various other electronic components which is added to this. And here on the bottom side, you can see what are all the components and the connectors being added. And next, going on to the cell screen, if I click on the cell screen top, it shows me what is the cell screen and what is the location like. And similarly, on the cell screen bottom also, we can see what are all the locations and how it is going to look. And here we can see the drill holes, what are all the different drill holes and how. Similarly, we can see the solder mass also. What are all the solder mass on the top of the board and on the bottom side of the board. We can find each of these parameters, and we can also get the copper layers. So how many copper layers, how it is going to look, and what are all the different things. So all these designs you can check depending on each and everything you can check. And here, in case, say, for example, if you want to see and edit any of these labels, if you can click R and once you enter here, you can see all the registers are being filtered out. And here, say, for example, if you want to edit any one of these, you can go to edit, and once if you go to the edit component, you can edit these components and right click, and say for example if you want to change its orientation, you can change it based on your requirement, 45-degree or 90-degree. So now I don't want to make any changes, so I'm just closing the component editor. So here you can see under edit option you have various options to edit your components, board outlines, mounting points, ICT fixtures, test points, mechanical parts. So you have the flexibility to play around with this. And then we have the pick and place and where we can check for each of our design parameters, how it is looking, what are the copper layers. Then we have the drill holes list also, we can find it out. And what are all the net lists? What is the net name and what is the rough disk and what is the pin name and what is the location of that particular component. And here you can see all the details are being captured here. And then we go to the analysis. So in the analysis, like I explained previously in my presentation, you have various options like component failure mechanism, the mechanical shock, natural frequency, random vibration, solder fatigue. So here, prior to that, I need to define my loads. What are all the different loads I am going to use? So here I already have a tutorial on the demo where we have included the define the loads. Say, for example, if you click on this, here we have defined the shipping load for between the frequency and the amplitude, what is the type of loading it's going to. And here you define the number of vibrations per hour and number of cycles per day. So all these profiles, you can define it here. Similarly, so on and so forth, we have added all the data. So here, after adding the boundary loading data, I'm going here. So I'm going to analysis and I go to clear analysis results. I go to edit properties here in the solder fatigue, and here we define the type of solder material what we are going to use. Depending on your requirement, you can select the solder material based on your design. And here you can select the thermal event, how it is going to behave. And you can save and run. Once you click on run, you can see a clock kind of symbol, which tells you that the simulation is running and now it has completed. And here, either you can directly double click on the solder fatigue to see the list of components. So here you can see all the, there are two ICs and a couple of registers which is being not meeting the design requirement or the set criteria. And whereas we have a couple of ICs here, which is in the border range. And then we have the various other components, which is meeting the design life and the expectation. So here you can see this details. And once you go to the life prediction, and here you can see like the red one is giving us a combined life of the board, and PTH is like the fatigue analysis, and random vibration fatigue and solder joint. So this solder fatigue is showing like it's having a very less probability of failure, and it can last up to 8 years. So here you can see there is no major thing. But when it comes to the random vibration fatigue, here you can see like in the in less than 1 year only, there is a chance for the probability, and it's not going to, it's not meeting our design requirements. So at that time, we need to make the design changes accordingly, and we can predict the life. Similarly, here plated through hole fatigue, you can see like how many holes are there, what are the results, and what is the PCB thickness, and what is the service life, and what is the probability of the failure for this plated through hole. So similarly, so on and so forth, you can edit and you can run it. And if you need in detail a demo or something to be given to your management, we will be happy to present our solutions and capabilities in detail to your team. So that's all I had for this particular webinar. And now the floor is open for question Q&A. Whatever questions you are having, please feel free to unmute yourself and you can ask the question.
I guess they won't be able to unmute themselves. I request you all to please type it in the chat box. Okay. Yeah, any questions, please?
Sandy, you can share that feedback form link also to the
Yeah,
attendees.
I have unmuted all of you. If you have any queries, please raise your hand. think you can unmute yourself and ask a question if required. Sharing across the feedback forms, the link to the feedback form. To request you to please fill it. If you have any queries, you can unmute yourself and ask us or type it in the chat box.
We will have the meeting window open for another 5 minutes. So in case if you have any queries or any doubts or if you need anything, please feel to unmute and ask us so that we can take it up. Sure, Divya, you can drop in your details with and you can give your details in the feedback form so that we will be able to share it across with you.
Other queries? I guess we can close the session.
Yeah, and we have not received any response on the feedback form. So I
Our
think
team
we
will
can
get in
start.
touch with them. Yeah, on a one-on-one basis, I guess our team will get in touch with you. So if you have any queries, you can please ask them. If you have any requirements, our Inside Sales team will get in touch with you. Thanks a lot for joining this webinar. We will be sending across the recording as well to you in a couple of days. Thank you so much.
Thank you.
Thank you.